All right. Okay, so the example that we've done so far deals with force acting on a wire, but that wire is just a single wire. There will also be cases where rather than having a single wire, we have two parallel wires. So here we have parallel current carrying wires. So when you have parallel current carrying wires and you place the wires close to each other, the wires would each experience a magnetic force, because one of the first thing I mentioned earlier in the lesson was that current carrying conductor or current carrying wires, because they have moving charge, they produce their own magnetic field, they behave like magnets. So if you have another separate wire which also carries current, so it will also have its own magnetic field. It will also behave as a magnet. So when you have two parallel wires carrying current, it's akin to you putting together two magnets close to each other. So you will expect both of them to experience a magnetic force. So when it comes to parallel current carrying wires, the nature of the force that they experience will only be two types. Either it is attractive, or either it is repulsive. Now, for case where the magnetic force acting on the wires are attractive, this one is where the current is same direction. For cases where the magnetic forces between the wires are repulsive, current is in opposite direction. Okay, so it helps to remember this because sometimes it will simplify your working. If your current is in the same direction, usually it will be attractive. But if your current is in the opposite direction, like the ones that you see here, the forces are repulsive. Okay, so that one is one thing to take note of. I think I wrote it here already in the other part of the notes, the next page of the notes. Okay, now how do we actually know this? Rather than just memorizing this one, we can actually try to predict the direction of the magnetic force to come to this conclusion. Now, if let's just say right now, I want to look at only this particular case where I have a pair of parallel wires carrying current in the same direction. Let's just say I look at for wire 1 only. I look at wire 1 only. If I want to draw the pattern of the magnetic field around that wire, this one is current going up. Now, do you remember that in the last lesson we mentioned that if you're just looking at the single wire, the wire itself produces its own magnetic field. The magnetic field is in the form of concentric circles whose direction can be determined by using whose direction can be determined using the right-hand grip rule. So if I look at wire 1 itself and I want to somehow draw out the pattern of the magnetic field, if I use the right-hand grip rule, on the left side, this one is where the magnetic field is coming out of the plane of the paper. On the right-hand side, this is where the magnetic field is going to the plane of the paper, right? Right? So this one is the pattern of the magnetic field of wire 1. Now, let's assume that we now have wire 2 in the picture right now. Wire 2 is placed somewhat near to wire 1. I could say that maybe wire 2 is right over here. It still has the same current, it still has current through it, which we call I2 through it. Okay, but now do you notice that if I just look at this one alone, this is a current carrying conductor. I see that there's current through it. I see that it's inside a magnetic field. This magnetic field is the magnetic field produced by wire 1. Okay, so you now have a wire with current inside a magnetic field produced by something else. So according to Fleming's left-hand rule, you should experience a magnetic force, right?
Yes.
Okay. So you can actually use Fleming's left-hand rule right now to predict the direction of the magnetic force acting on wire 2. So you use Fleming's left-hand rule right now to predict the direction of the magnetic force acting on wire 2. Your B is into plane of paper or plane of screen. Then your I is pointing outwards. You will notice that your FB is actually going to be pointed towards the left, correct? Okay, so this one is from Fleming's left-hand rule. Now, your case here is that this wire experiences a magnetic force because of the interaction with wire 1. So if you try to pull in Newton's third law into this, you will also say that because these two objects are interacting with each other and it causes one of the objects to experience a force, the other opposing object must also experience an equal opposite force. So here, you're going to get an FB also, but equal opposite direction. This one is from Newton's third law. Okay, so that's why you see here, your force is like this. Okay, that's why we could say that for a case where the currents are acting in the same direction, your magnetic forces are attractive. Okay, now this analysis can also be repeated for the other one. If you repeat the same analysis for the other one, for the other example where the currents are acting opposite direction, you will eventually come to the same conclusion that the forces are acting in opposite directions. You will eventually come to the conclusion that the forces are repulsive. Okay, right? So that's what you want to do. That's what you should understand. Do you want me to show it for the second diagram also?
No.
Okay, so you understand the concept is just based on this now. All right, that's how we can say that the forces are attractive and repulsive for forces are attractive or repulsive depending on the direction of the current. Okay, right. Then after that, another thing that we need to mention here is this. Now, for the two wires I1 and I2, for the two wires with their currents I1 and I2, you could have a case where the current flowing in both wires are different, but the magnitude of the force experienced will always be the same. This is because of Newton's third law, which states that all forces between the forces between two bodies must be equal opposite to each other. All right, so just bear this in mind now. Okay, because the questions do sometimes ask you, what if the currents are different? Will it cause the force experience to be different? The answer is no. The force experienced by both wires will always be the same because of Newton's third law. There's a way to prove it using calculation. That one is actually shown here below. Now, earlier in the lesson, I mentioned to you that B is KI over D, or I believe is mu naught over 2 pi times I over D. This one was for the B for a wire. And this is the magnetic field strength or magnetic flux density for wire. It's actually from this part of your notes under page 2. Yeah, page 2. Remember this one I mentioned to you, if you want to talk about the magnetic flux density of a wire, is this equation here. But I also mentioned specifically to you that you don't really need to remember this equation, because if it's required in your exam, they will tell you. Okay, here I'm trying to use back that same equation to show you why the forces are the same, even though the currents are different. Okay, so B for a wire is this. FB for a wire is going to be this, provided that the currents are the same lah. Provided that the wire is perpendicular to the field. Okay. Now I want to apply these two to my case here. Okay. Now let's just say that for I2 right now, I want to talk about the force, magnetic force acting on wire 2. I can say that the magnetic force on wire 2 is B1 I2 times L. Okay, just for wire 2. Okay, so the magnetic force on wire 2 is B1 times I2 times L. L is the length of the wire inside the field. I2 is the current flowing inside the wire. But why is it that I specifically put B1? The B1 here is because wire 2 is inside the magnetic field caused by wire 1. Okay, so this one is B1 because my wire 2 is inside the magnetic field of wire 1. Now, if I try to expand this, if let's say I just use K, this one is I1 over D times I2 times L. This one will give me K. This one will give me, let me just rewrite this properly. This one will just give me K I1 I2 times L divided by D. Okay, so this one is for magnetic force on wire 2. Now I can also do the same analysis for wire 1. Okay, this one is for wire 1. Now if I try to do the analysis for wire 1, you can try and think of it as this. Wire 2 will also produce its own magnetic field. Okay, so if I use right hand grid rule on wire 2 alone, this one, the magnetic field is going in out of the plane of the paper for the left side, and then going into the plane of the paper for the right side. Now for wire 1, is inside the magnetic field of wire 2. Okay, so we know that you give you a magnetic force in this direction. When we want to calculate out the magnitude of the magnetic force on wire 1, we can actually say is B2 I1 times L. B2 because the wire 1 is inside the magnetic field of wire 2. So this one I can expand it. I'll get K I2 over D times I1 times L. So this one will become K I1 I2 times L divided by D. So you notice the expression for both of them are the same. Even though the currents are different, you're going to get back this same expression. All right. So this one is something like a mathematical proof why the forces are going to be the same, despite the fact that the currents are different, because they are the product of each other. F2 will be the product of the currents, F1 will be the product of the currents. So you will always get back the same magnitude. Okay, but it's easier to just say it's because of Newton's third law lah, right? That is the easiest one to understand. Okay, so that one is for parallel wires. So parallel wires were done. Then we can do some questions on that before I move on to the next major part of the chapter. Okay, parallel wires would be page 38. Okay, wait, now let me have a look at that. Okay, we look at page 38. Okay, so I'll just close whatever. Okay, maybe I should close that one. Okay, have a look at page 38. Okay, maybe it's better. Just, yeah, have a look at page 38. Okay. So they tell you you have a long straight vertical wire that carries a current of I, while the wire passes through a horizontal cut EFGH as shown in figure 8.1 and 8.2. So they're asking you right now on figure 8.2, draw the pattern of the magnetic field produced by the current carrying wire in plane EFGH. They want you to draw the pattern of the magnetic field caused by the wire. Okay, so this one is November 9, 241. We go to that one. So by now you should know you will need to use your right hand grid rule. You need to draw a pattern of concentric circles. So the direction is indicated by your right hand grid rule. So the direction is going counterclockwise. Okay.
Yes. Joe, do I need to use
Compass?
a
Yes.
compass? Yes.
I would suggest you bring a compass along to your exam hall. Okay.
Okay. All right.
Because you see this one here, when you want to draw the circle, I also mentioned that when you draw the circle, you need to make sure that the line spacing is increasing. Like you notice that this one versus this one and this one, the line spacing is not the same. So this is another thing that you need to be mindful of. Okay, you see this one is for 3 marks. So 1 mark comes from you drawing a pattern of concentric circles. 1 mark comes from you showing the correct direction. 1 mark is given for you showing them in increasing spacing. Okay, so this one is Fleming's right hand. Sorry, this one is predicted using right hand grid rule. Okay, for magnetic field around a wire. Okay, so now you look at part B, they tell you two long straight parallel wires P and Q are now situated at a distance of 3.1 centimeter apart, as illustrated in figure 8.3. You now have the two wires situated 3.1 centimeter apart, and they're parallel to each other. They tell you current in wire P is 6.2, current in wire Q is 8.5. The magnetic flux density, yeah, that's clear of everything. They tell you that the magnetic flux density B at distance x from a long straight wire carrying current I is given by this expression, where mu naught is the permeability of free space. So this is the part where I told you earlier, if they want you to use this form of your equation, this equation in page 2, B is equals to mu naught I over 2 pi d, they will specifically give it to you. You don't need to remember the equation itself. They will give it to you. Okay, so when mu naught is the permeability of free space, so from here they ask you calculate the magnetic flux density at wire Q due to current in wire P. Okay, so this one, what is the flux density at wire Q due to current in wire P? So you look at this one, this is wire P just now, this is wire Q, all right? They want the flux density at wire Q due to current in wire P. So as I mentioned to you, a current in one of the wires will cause a magnetic field. So that one is indicated by these green dots here. The current in wire P will cause this magnetic field here. And it so happens that wire Q, the orange line, is inside the magnetic field of wire P. The question is now asking you to find out the flux density at wire Q due to current in wire P. So what you're trying to calculate here is actually the flux density of wire P itself. So you can use B is mu naught I over 2 pi x. Your x is actually 3.1 times 10 power 3.1 centimeter. The question actually already did give you that. You look at this one, they tell you that the wires are situated 3.1 centimeters apart over here. So you know that this distance here is going to be 3.1 centimeter. Right, so just calculate out and you're going to get the answer. Okay, so this is one part. Now then the next one asks you to calculate the force per unit length in Newton per meter acting on wire Q due to current in wire P. So first part they ask you what is the flux density at wire Q due to current in wire P. Now this one they ask you what's the force acting on wire Q due to current in wire P. So as I mentioned earlier to you just now, because this wire Q is inside the magnetic field of wire P, and at the same time you have current flowing through wire Q, you're going to have a magnetic force being produced. So the magnetic force will be in this direction if you use Fleming's left hand rule, following the example that I just did just now for you. But right now, we are not really concerned with the direction yet. We just want to find out the magnitude. So if I want to find out the magnitude of the magnetic force on wire Q, remember I mentioned you can use this FB is BIL. Okay, so since they want force per unit length, you just shift the L to the left side. So it becomes FB over L. Then you're left with BI. Okay, so your I here must be the current in wire Q. Your B here must be the flux density of wire P. Okay, so you get these values. No? Your flux density due to wire P was 4 times 10 power minus 5, which you have here. Your current inside the wire is 8.5 ampere, which is this one. Then you'll be able to get the answer. Okay. All right, so this one should be okay. Right, so if this one is okay, then you look at the part C here. They tell you the currents in wire P and Q are of different magnitudes. All right. Still explain whether the forces per unit length on the wires will be different. So the current here already is shown to be different. They now state to you that the currents are different. Would the different current cause the force per unit length on the wires to be different? Would they each experience a different force? So just now I mentioned to you earlier, the forces will always be the same because of Newton's third law. So you can just say something along these lines. According to Newton's third law, force on Q due to P is equal opposite to force on P due to Q. Thus, the forces have same magnitude. Okay, so this one is the easiest one to somehow say.
Yep.
There's also another one in red below here, where they say to you that the force per unit length is proportional to the product of the two currents, therefore same magnitude. It's actually referring to that little mathematical derivation that I just did, where eventually you get this one. Just now in the notes, I showed you the derivation of the forces, which is this one here. I managed to show you F1 and F2 actually have the same expression, and they're always the same as they're always directly proportional to the product of the currents. Your answer here is saying that, okay? But usually I wouldn't use this answer. This one is like a bit complicated. Yeah, although you can just write this one is a bit hard to understand unless you derive it. I would say saying Newton's third law is the easiest one. Okay?
Okay.
All right, so this one is okay. Then the next one will be 51, page 51. Yeah, basically 4 questions, 3 questions now. Okay, 51. Let's have a look at 51. Okay, so 51 is also on parallel wires. Yeah, parallel wires is a question that has been coming out quite recently. Last time in the previous years, they didn't come out a lot. They didn't really come out a lot, but in the recent years, they've been coming out quite a lot. So parallel wires is something that you might want to make sure that you are familiar with. Okay, right. So have a look at this one. This one will be page 51. Okay, so have a look at page 51. Okay, page 51, same thing as before. All right, so this one, I think this one will just breeze through it very quickly. Okay, you have long straight wire, long straight vertical wire A that carries current in outward direction. The wire passes through the center of a horizontal card. The card is now viewed from above. The card is shown from above as shown. On that same figure, draw 4 lines to represent the magnetic field produced by the current carrying wire. So if current is coming out of the plane of the paper, use right-hand grip rule.
Yep.
Direction will be counterclockwise. And here the question asks you to draw 4 lines. They specifically ask you to draw 4 lines. So draw the 4 lines. Make sure the spacing is increasing.
Yep.
So this one is okay.
Yep.
Now, same thing. If you look at part B, the next page, 2 wires A and B are now placed in the card. The 2 wires are parallel and carrying currents in the same direction as illustrated in figure 10.3. Explain why a magnetic force is exerted on each wire. So this one is, they want you to explain why a magnetic force is exerted on each wire. You can say something like this lah. Current in each wire produces a magnetic field on each wire. Each wire is in the magnetic field produced by the other wire. As current in each wire is 90 degrees to the field that it is in, a magnetic force is produced. Right, now let's take the directions of the forces. So now, just now I mentioned to you, since you see that the direction of the current is in the same direction, the forces ought to be attractive. All right. So earlier when I taught you the parallel wires portion, I mentioned that if current is in the same direction, forces are attractive. If forces are in, so if current is in opposite direction, forces are repulsive. You could also actually try to analyze it one by one by using Fleming's left-hand rule and Newton's third law, but that one is actually going to take you time. All right, so it's easier just to remember that. Okay, but if you want to like double check to see whether you were correct, you can do the analysis like what I did just now. Right, so that one was okay. Now, then after that, C, the currents of the two wires are not equal. Explain whether the magnetic forces on the two wires are equal in magnitude. Again, this one is same like what we just did. According to Newton's third law, the forces should be equal in magnitude, equal and opposite in magnitude. Okay? Okay, so this one, okay. The other answer, force is proportional to the product of both currents, thus forces are equal in magnitude is the same thing as what we did just now. So, but this one I mentioned better not to use this now. Okay, I go through the last question before I move on to the next part of your chapter. Have a look at page 4. Okay, page 4. This one is November 15, P43. Okay. Okay, so November 15, P43, there's one question. Okay, so if you look at page 4 of your notes, this one. So I'm just gonna look through this one. Okay, they tell you suggest an explanation for each of the following observations. If you have two wires that are laid side by side and carry equal currents I in opposite directions as shown in figure 6.1, why is it that the total flux density due to the current in the wires is negligible? Basically, what they're trying to ask you right now is that why is it that when I have these two wires with current in opposite direction laid side by side, the magnetic flux density or the resultant magnetic flux density is 0? Basically, it's saying this. Why is the resultant B 0? They say here total lah. It's actually referring to the resultant. Why is the resultant magnetic flux density due to the currents in the wire negligible? Okay, let's go with this one. Just to show you something. This one I need to draw on the diagram. Let me just draw this thing on to your diagram first. This one I'll probably draw on the left right hand side just to show you what's happening. Okay, if I try to draw the wires out for you right now, this one is the first wire where your current is say going out.
Yeah.
This wire produces its own magnetic flux density. It produces its own magnetic field, which according to right-hand grip rule, this one is B field going out. This one is B field going in. Okay, so this one is okay. Now, if I go through the second wire, which is this one, where I tell you that the current is going opposite direction, you can say that all the magnetic flux, the magnetic field crossed by this wire, on the left hand side, it will be magnetic field going out of the plane. On the right hand side, it will be magnetic field going into the plane of the paper. Okay. Now you see, if I have a separation D here, some sort of separation between them. Now, what can I say about this particular region? Wait, am I doing this correctly? Yeah, this one is current going opposite direction, right? The total magnetic flux density due to the current is negligible. Why are they? Oh, okay. I drew this one wrongly, sorry. This one, if I use right hand grip rule, because the current is pointing downwards, right? The left hand side would be where current is going into the plane of the paper. Sorry, magnetic field is going to the plane of paper, and then magnetic field is going out of the plane of the paper on the right. Okay, this is the correct pattern, right? If using right hand grip rule.
Yes.
Okay, right now, if you look at this center region now, notice that this one is going to the plane of the paper. This one is also going into the plane of the paper. Do they cancel each other off, or are they kind of strengthening each other?
Yeah, kind of strengthening each other.
Yeah, so this one is strengthening, right? So B cannot be 0, right? Because they don't seem to be canceling each other off. They seem to be both moving in the same direction. They are reinforcing each other, strengthening each other, right? Okay, so this one here, when you look at this one, and then they tell you that the flux density due to the current in the wires is negligible, kind of seems contradicting, because what you can see here is that they seem to be strengthening each other. Now, there's a keyword here that a lot of people tend to overlook. They say that the wires are laid side by side, meaning to say they are very close to each other. So now, if I have the same wire, notice what will happen if I lay them side by side. This is the same wire. If I lay it side by side with no D between them, this is what I'm gonna get. I'm just drawing the same thing again. It's dot, 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 cross, cross, cross. And then this one here, I draw the wire like this. This one is where my current goes down. So I draw something like this. This one is dot, 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 cross, cross, cross. Okay, so from here, what you want to see is this one. What color can I use? Maybe I use green. Now I see this one. This one is going out. This one is going in. And then after that, you look at the opposite side, this one. This one is going in. This one is going out. So you see, these two are actually opposing each other. Opposing or cancelling each other.
Okay.
Therefore, B can be 0. Okay. Yeah, in the first place, how can I say the B are equal opposite? Now, it's correct to say that B depends on I, right? Your magnetic field strength or magnetic flux density depends on I, because B is K I over D. I mean, just using common sense, we will know that B depends on I lah. Okay? So another thing here that you could probably be aware of is this. They tell you they carry equal currents. So if they tell you equal current, that means equal B. Then after that, if the wires are laid side by side, that mean that B is in opposite directions for both wires. Okay, just based on these two facts alone. Because you have equal current, you have equal B. And then because the wires are laid side by side, B will be in opposite directions for both wires. So as a conclusion of this, you will say that B is equal and opposite. Therefore, resultant B or total B is 0. So I'll show you the answer. It only makes sense after I explain this. The answer was this one here. The ones that is written in pencil here. Okay, let me just highlight it. They tell you that the magnetic field strength or magnetic flux density due to the currents are equal in magnitude in opposite directions. The fields will superpose to give you 0 resultant field. That's it. Okay, this was the answer that they gave. But how do I know they are equal in the first place? They're equal in the first place because you have equal current. How do I know they are opposite in direction in the first place? They're opposite in direction because they are laid side by side. And then because of these two facts, they will cancel each other off. Okay, so it's this one here. All right, so this one okay?
Yeah.
Right, so this one is okay. Then I move on to the next part of your notes.